Okay, wonderful. All right, welcome everyone to DDPS seminar. Before we introduce our invited speakers, let's go over some rules and logistics as usual. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute yourself and ask those questions. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. So please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. Okay, that's about it. Now let me introduce our speaker today. It is an honor to host Matthew Zahr, who is an assistant professor in the Department of Aerospace and Mechanical Engineering at the University of Notre Dame. He received his PhD in computational and mathematical engineering from Stanford University in 2016. I happen to be at the same PhD program, and there was an overlap with Matt. And when I was, with Matt at Stanford, he was really smart student. And also he was really hardworking person. I mean, I know that from my experience with him, and obviously, naturally, he accomplished a lot, and he was a Louis W. Alvarez postdoctoral fellow in the Department of Mathematics at the Lawrence Berkeley National Lab from 2016 to 2018. And Matt, you got the early career award from somewhere, right? Like the
Air Force.
Yeah, and he's the recipient of the early career award from Air Force, and his research interests include high-order methods for computational physics, Pde Constrained Optimization, model reduction, computational methods for resolving shocks and discontinuities, and multi-scale methods. Okay, today Matt will present model reduction of convection-dominated partial differential equations via optimization-based implicit feature tracking, which is a great interest to us. So please enjoy and expect a wonderful talk from Matt. Now, without further ado, let me pass the baton to Matt by asking one random question, as usual. Okay, today's random question is, what is your favorite TV show?
My favorite TV show? Do I have to answer that now or do I answer it at the end?
You answer right now, and then well, you need a time to think about it.
I don't know. I was a big Game of Thrones fan when it was especially during the earlier seasons. So I guess I'll say Game of Thrones. It's HBO, so I don't know if that counts as TV or not, but I'll go with that one. So
okay, that's legitimate answer. Thank you, Matt. It's all yours.
all right, sounds good. Thank you very much for the introduction, Young-Soo, and the invitation to talk here. So I'm going to be talking about model reduction of convection-dominated flow specifically, and obviously the interest in convection-dominated flows is that they arise everywhere in engineering analysis and design, specifically, especially when you have fluids and fluid flows. I'm in an aerospace department. I spend most of my time thinking about aerospace applications. So these problems are obviously everywhere in these fields, and these really constitute some of the most challenging simulations that we do as computational physicists, because they have very strong shock waves. They can potentially have turbulence associated with them. If you're in very high speed regimes, you can have to account for chemical interactions and ionization. They can lead to very complex and very computationally demanding simulations. So that's where, if we want to use these to drive optimization or uncertainty quantification, it just becomes impractical. And that's where kind of model reduction comes in. And unfortunately, when you try to apply a model reduction to these kinds of problems, they face serious limitations. So I have a little, kind of, probably many people have seen little demos like this, and because this is a fairly hot topic now, but I'm going to do it again just to demonstrate the point here, is that we can boil this down to a very simple 1D problem. So we take we solve our CFD problem and get one snapshot. We solve it, we change the parameter in some way that discontinuity moves, and now we would like to approximate something that's in between them. Now, this is something that we would hope that we can do. We sample our very expensive high fidelity model on the endpoints of some parameter configuration, and you would like to get it in between. And unfortunately, if you're just going to be doing linear combinations of these black curves, the best that you can do is this jagged staircase approximation, which I think, regardless of whether you're an engineer or a mathematician or anyone, I think we can all agree that this is a pretty crappy approximation that we're not going to be happy with. So this essentially is the issue, and this comes up as the slowly decaying Kolmogorov in width. You add enough samples in here between these two black curves, and you're going to eventually get a decent approximation, but you need a bunch of them. So that's the fundamental problem. And this is what I'm going to be introducing methods to address in this talk. But before I do that, I'm actually going to spend the first half of the talk talking about a problem that is essentially the exact same problem in a different context, and one of my solutions to that, and then port it over to the model reduction setting. So if we look at this exact same problem arises when we look at just standard finite element based discretizations of the same kinds of problems, these convection dominated problems. So I'm going to do the same thing. We have a mesh, a 1D mesh that consists of two elements, and here's our basis now. Before, our basis was these nice global basis functions, but in the finite element setting, we have these local, potentially high order polynomial basis functions. You want to approximate a discontinuity now, and everything is fine in the first element, but then you get these oscillations in the second element. It's a terrible approximation, first off, and the oscillations can actually cause the codes to crash. So this is a problem that's been around forever in CFD. So the way that people deal with this is there's a number of different ways. One is that you do something called limiting, where you say, I don't want to allow all those high order oscillations, so I'm just going to crush them and reduce this to a first order approximation here. And that's fine. It addresses the kind of the overshoot undershoot issue, but it's obviously a pretty crappy approximation still. So you have to add in some mesh refinement near the discontinuity, and you can get a decent approximation. The downside of this is that we just went the opposite direction of model reduction. Instead of trying to make things cheaper, we made it more expensive to have to refine in these regions. So another approach is artificial viscosity. Say, I don't want to deal with discontinuities. I would much rather deal with steep features. So we're going to replace the red with this steep feature magenta curve and try to approximate that. Your oscillations are reduced. Still not a great approximation, so you still have to enrich with refinements of your mesh. Again, kind of going the opposite problem from reduction. So another class of methods that I've been working a lot on is called shock tracking. And really the fundamental idea behind shock tracking is that we have a feature in the solution. That feature right here is a discontinuity. That same feature exists in our basis. That's that we have a discontinuity that we can support between these two elements. The problem is the feature's in the wrong spot. It's the exact same problem that we had in the model reduction setting. Our basis actually had that shock that we needed in it, but it was in the wrong spot. And when we tried to use it as in our basis, it didn't give us a good approximation. Same issue happens here. So the idea behind shock tracking is that if I can deform my mesh such that the interface between the elements lies at that discontinuity, now the discontinuity in my basis is aligned with the discontinuity in my solution, and you can just nail the pretty much the exact solution in this case. Now, if it's not piecewise constant, you won't necessarily get the exact solution, but you get approximations on really coarse meshes. So to kind of take the motivation for this kind of tracking method further, because that's the idea that we're going to be employing in the model reduction setting, is that one of the benefits of this is that you can actually recover optimal convergence rates of your underlying scheme. Everyone probably is familiar with it. If you do a finite element method, you're going to get these order h to the p plus 1 optimal convergence rates, but that only is for smooth solutions. But if you actually track the discontinuity, the finite element basis does not see the discontinuity at all. You're just using those higher order basis functions to approximate away from the discontinuity, and you can recover optimal convergence rates. Another kind of taking this a step further is that why we actually care about doing this in the high order setting. And I really think about model reduction as kind of like the ultimate high order method, because with high order methods, we try to make coarser meshes that have inside each of these elements, these larger elements, high order basis functions, so we hopefully can reduce the overall number of degrees of freedom. ROMs take that to the extreme where you really have just one element that has all these global basis functions in it. So it's kind of in the same spirit here. Anyway, but the point is that when you do shock tracking with higher order methods, there's an exaggerated benefit. So what I did is I ran two studies here. First one was I just used a standard kind of shock capturing method with very aggressive mesh adaptation in the vicinity of the shock. And that's what these red curves, or the dashed curves are. The solid curves are when we do shock tracking, and these are for the different colors mean different polynomial degrees. So if you look at the difference between the dashed and the solid black line, there's an improvement for doing the tracking approach, but it's not ridiculous. But if you start to look for P2 or P3, you're talking about 5-6 orders of magnitude improvement. So this idea of tracking really helps you a ton in the high order setting, whereas it helps in the low order setting, but the benefits are exaggerated in the high order setting. And to take this kind of a step further is that if you just look at the solutions you get by tracking the discontinuities, I mean, this is supersonic flow over a cylinder. And if we use a P2 mesh, which we have right here, I mean, you can get basically the exact solution with less than 50 elements. Whereas if you're going to be doing this with shock capturing, you would have tons of refinements around the shock here, and you would have thousands or maybe even tens of thousands of elements for this kind of problem. So that's my kind of pitch for why shock tracking is kind of a relevant thing to do. But the next question should be, well, why do people not really use it in most of modern CFD? And the answer is that it's pretty hard to do when you have complex problems. So you have this little scramjet here, you have some usually hypersonic flow would come in here, or a high Mach flow would come in here, and you get all these shocks that bounce around, and you'd have to somehow align your mesh with all these shocks, and you don't know them, by the way. You don't know where these shocks are. They're a function of the solution. You know the boundaries, but you don't know the internal boundaries like that. So problems like this have been kind of where shock tracking has kind of not been able to make a big impact. And this has really been where I've been putting a lot of my research effort in the last few years, is developing methods that can specifically overcome this difficulty associated with explicitly trying to mesh these unknown discontinuity surfaces. Okay, so that's my overall pitch for shock tracking. So what I'm going to do for the rest of my talk is I'm going to spend about 15-ish minutes talking about our approaches for actually doing shock tracking without even talking about ROMs. And then I'm going to bring that into the model reduction setting and connect it to what we're doing. So that's the kind of the outline of the rest of the talk here. So looking at the shock tracking method that we've been developing, as I mentioned, the goal really is to align your mesh, the faces of your mesh, with your discontinuities. And so we can see another example here of if you don't do any alignments and you want to represent this piecewise constant function, you don't do such a good job, but once you align it, you can nail it with a really coarse mesh. So the method that we've been developing is based on a DG discretization, because for two reasons. The first is that we have these inter-element jumps. So if we get those faces aligned, the jumps capture the discontinuity, and then they're high order. So I tried to make the case for high order a few minutes ago. Now, the innovation of the approach here, and this is exactly the same thing that we're going to be porting into the model reduction setting, is that we don't treat this as a mesh generation problem. Even though it technically is, because you need a mesh that conforms to all these interior shock boundaries, we don't treat it that way. What we do is we create a mesh that it doesn't know anything about the shock, just comes out of unstructured mesh generation. And then we set up an optimization problem that drives the mesh toward one that aligns with shocks. That's the difference here. So we don't think about this as mesh generation. We think about it as optimization. And then we come up with solvers to solve these optimization problems. So to see what that looks like, we're going to start with just the kind of the formulation. We have some sort of a conservation law. I write it as steady state. If you want time dependent, you can write it in a space-time setting and use slabs. We then discretize with DG in this case, and we get this kind of standard DG form with your numerical flux function in here. If we write this in algebraic setting, we get this fully discrete residual, which is going to depend on your fully discrete coefficient vector of your flow that contains your flow field, as well as the nodes of your mesh, right? Because we need that to explicitly show up on our residual, because we're going to start moving these around. We also introduced this thing I call capital R, which is where we actually enrich our test functions. So P prime is the polynomial degree of your test functions. We take P prime to be P plus 1 in the definition of R. So we're bumping up the number of test functions that we have per element, and we're going to use this to define our objective function that is in our optimization problem. So here is the formulation that we have, very standard Pde Constrained Optimization look to it, something that me and Young-Soo worked on way back in grad school on a bunch of different applications. And so here's what it looks like. So our constraint is the DG equations, the standard Galerkin DG equations, with P, the test and trial space, equal degrees. And the reason we put that there is because we want this method to inherit the properties that we like about DG. It's high order accuracy, it's consistency, conservation, all those beautiful properties we want. So by putting them as our constraint here, we're going to get them. Then our objective function is going to be composed of two terms. The first one, or the second one, is going to be this R mesh term, which is just kind of the obvious requirement that we don't want our mesh to degrade. We want to retain a fairly high quality mesh. And then this other one is this enriched residual, where we've added on these test functions. The idea is that they will penalize non-physical oscillations that would arise from solving on a non-aligned mesh and then drive the mesh toward one that is aligned. So that's what the optimization problem is. Now, we can't, actually going back, we can't solve this using what people would call a reduced space approach. That's kind of the go-to in Pde Constrained Optimization. You would want to, like at least what I would want to, given my background in Pde Constrained Optimization, would be to update the mesh, solve the DG equations, and then plug that in here, and you can have an unconstrained optimization problem, which are easy to work with. You can get gradients and stuff using adjoint methods, but that won't work in this setting because we cannot solve this DG equation for any mesh. If the mesh is not aligned, we can get these oscillations that cause it to crash. So we can't use reduced space approaches, so we do a full space approach, which means we lump U and X into a combined vector that I call Z, and we update that whole thing together until we converge to a solution of the optimization problem. And to do this, we use sequential quadratic programming. So at every iteration, delta Z is computed as the solution of a quadratic approximation to our original Pde Constrained Optimization problem. And then so there's a lot of details that go in here. We need some approximation to the Hessian of the Lagrangian, and we choose the search direction using a line search technique. I mean, I'm not going to go into the details of that in this talk, but this is essentially how we do that. So to look at a few of how this works, we start with a very simple application, which is just advection in a. It's not going to work. You can hear me. Hold on a second. Accept. Okay, there we go. So we have a very simple application where we have just advection in a 2D domain. It's a step function over here, and the advection field is pointing to the upper left. And you can see I just showed the shock tracking iterations. We start from just a solution that is a mesh that knows really nothing about the discontinuity, first order finite volume approximation to start, and then here's where how the shock tracking approach works. So we can see that we get really rapid convergence to the optimal solution, Newton-like convergence, less than about 10 iterations, and we get to essentially machine tolerance. And the thing to note here is that this is where you can see the full space method in action, because the residual, the little r, the DG residual, is only 0. I mean, it's technically 0 at the beginning because we started with the finite volume solution, but it's not 0 until the very end. That's all you're guaranteed with full space methods. If you were going to be doing a reduced space method, you would be having this little r 0 the whole time, right? So that's the kind of how these approaches work. But again, for this problem, the reduced space approach would work because it's linear advection. It's not going to go unstable and blow up on you. But it won't work for more complicated problems like that involve the Euler equations. Same kind of problem, but now we have a spatially varying advection field. Pretty rapid convergence to the solution here. Can do it in 3D to get these kind of tracked fields, even if you have these curved tetrahedral elements. So to look at a more interesting example, it's 1D now, but it's the Euler equations, where we have flow through a nozzle, and this is the density distribution that you get. First thing we do is we solve this with shock capturing. We put down a mesh that has 50 elements, and we refine and we get this solution that's pretty much perfect everywhere except for the shock region. You approximate the discontinuity with this steep gradient. We're going to do shock tracking now. We're going to put down a much coarser mesh, and we're going to solve the shock tracking equation, and you're going to eventually get these as your inter-element boundaries, and you can see you've got one that perfectly aligns with the jump here, and the yellow is, which lies right on top of the black, is the approximation. And then looking at convergence rates of this, you can see that we actually recover, again, these optimal convergence rates up to P5. Whereas if you do shock capturing, the error is going to be dominated right at the shock, and it's going to be limited to essentially first order convergence. So that's again the benefit of doing the shock tracking approach. Now, one thing that I haven't mentioned yet, and this is going to be important not just in this setting, but really important also in the ROM setting, is that I can't optimize the nodes like I said so far. If you optimize the nodes directly, all of the nodal coordinates, you're going to have nodes on boundaries that are going to fly off boundaries as the optimizer starts to try to figure things out. And now you've just changed your problem, and it's essentially meaningless. So we have to essentially enforce the boundaries remain boundaries, the same boundaries that they started as throughout the whole mesh motion process. So to do this, what we do is we introduce this mapping phi, which is going to guarantee that the boundaries are preserved. So instead of optimizing directly over the nodal coordinates, we're going to introduce a collection of unconstrained degrees of freedom that I can freely change and tweak and however I want to, and then plug that into my mapping, and my mapping is going to output me something that will conform to my original boundaries. So then the modification of the tracking problem becomes very simple. I just, everywhere that I had X, I replace it with phi of Y, and I optimize over Y. So to see what this looks like, I mean, if we go down to this very simple mesh down here, all of these blue nodes are interior. I can move those in X and Y however I want to. And you can see that they can move freely in X and Y. But for example, on this bottom boundary, you can only move in X. If you move it all in Y, you're changing that bottom boundary. So that's where your unconstrained degree of freedom would be your X coordinate, and you would use this mapping to determine what the Y coordinate has to be. Similarly here, you can't, this is not just move X or Y. You have to move, let's say, pick one of them, and then for example, the Y coordinate then would be given in terms of the X coordinates. And then, for example, at intersections of boundaries, those nodes can't move at all. So this can all of these cases can very easily be worked out from just looking at the normals of the boundaries. In the case where all of your boundaries are planar. When your boundaries are curved, you have to actually know the curvature, the expression for the analytical expression for the boundaries. So for here, again, we can still move all these nodes. It's not like they have to remain frozen, but they need to slide along their appropriate boundary. Anyway, this is something you can do. We have an archive paper on this that we just put out a month or so ago that can be used to do this. So just to show how this method works on a few examples, I'll show Mach 2 flow over a cylinder. We already kind of saw this one in a half domain earlier. We can do Mach 3 flow over the cylinder using the same starting mesh. This kind of shows this is kind of robust to meshes. Whereas if you're doing this with shock capturing, you would need to have different refinement regions about these two different areas to be able to really be able to change your Mach number like this. We can do Mach 4 flow over this curved cylinder thing. Over this curved square thing. We can do some transonic cases. This one, you have to actually be able to slide along this curved boundary of the Noc Airfoil. And then kind of exact same mesh, we went from Mach 0.8 to Mach 2. We do supersonic flow to align with the shocks there. So I'm going to skip over a few of the details. We have to be able to allow elements to collapse out of the mesh, because when you have really complicated problems, it's hard to actually just move nodes around and get things to align. So that we have to be able to remove elements. We do very simple operations called an element collapse, where we essentially say we have an element that's an edge that's too short, so we collapse that edge and remove it from the mesh. That's the only mesh operation that's topological in nature that we have to do. So let me skip over a few of these things just because I don't want to spend too much time on this. The other practical consideration I have to do is that when you have high order approximations, you can have oscillations that arise. So this is just an example of an oscillation that can arise when you're doing this tracking. If you just leave it alone, it's going to lead to terrible SQP search directions. And this is one of if you have this as the state of your mesh and your solution, this will be your next iteration, even after doing a fancy line search on an L1 merit function. So it really, the oscillations spread to neighboring elements, screws up your mesh. It's just not good. So you just have to sit around and hope that those elements kind of get collapsed out. So what we do instead is we just say, I don't want to deal with these things. So we go through and find the elements that are oscillating using a very standard indicator, and we reinitialize them to an average value, and then we continue the SQP iterations from there. And it has a pretty big impact. If we don't do reinitialization, we get stuck here with these oscillations inside these elements that don't go away, and then you don't get things tracked at wherever they arise. But if we do the reinitialization, like I just mentioned, those just get pushed out of the solution, and it does not impede tracking. So then to just last thing I want to say on this before I show a couple more examples is that how do we actually get an initial guess, right? We're doing non-convex Pde constrained optimization. So the initial guesses are important. So what we do is we, the mesh, we don't know where the internal boundaries are. So really the best we can do is whatever the mesh that comes out of the mesh generator, whether that's a structured mesh, because it's a really simple domain, or it's an unstructured mesh, whatever that is, that's what we use as our initial guess for the mesh. Our solution, we tried a bunch of fancy things here. The one that turned out to be the best was just use a P0 DG solution, or a first order finite volume solution. So that's why for that Berg's equation I just showed, this is where we start. And one of the things these robustness measures, the element collapses and the reinitializations have done, is that we do not need to use homotopy in the polynomial degree. Before we had these, we had to start at P1 and then go to P2 and slowly ramp up. But now we just, whatever polynomial degree we want, we go straight there from this approximation. So whether it's P1, where we have these faceted approximations, or P4, we don't do any sort of homotopy. Okay, so just to show couple last examples. So here's just a standard sod shock tube. We start with just a jump in the solution, and you have these waves, a shock, a contact, and a rarefaction that emanate from that point. So this is just what the solution looks like. But if we solve this with shock tracking, we're going to use a space-time formulation, as I mentioned before. And here's what our solution looks like, the tracking iterations look like. You see that initially the shock was tracked pretty quickly. Then you get the contact next. And then you even get the head and the tail of the rarefaction that tracks. So it's not only discontinuities that get tracked, it's also steep features. It's also non-smooth features, including jumps in derivatives, even when the solution is continuous. And then there's the solution without the mesh. And then you can see slices from the tracking aligned pretty well with the exact solution. So a more interesting example, and actually one of my favorite ones that we've done so far, is just 2D steady Euler equations flow over a diamond. And we'll run this one, and you see what's going to happen here is that we have a shock that's going to come up, it's going to reflect, and then it's going to intersect with the shock down here, which is going to then intersect again. And by doing this full space approach where we just iterate both the mesh and the solution together, we can get fairly complex shock interactions out of this. And we can get them tracked. And then without the mesh, you have this approximation. So taking that same example a little bit more in extreme, higher Mach number, more complex geometry, we kind of see similar behavior. We can get the intersections and the reflections and the curved shocks out of this. Takes a few more iterations, requires a bit finer mesh in this case, but kind of eventually converges to a reasonably aligned mesh. Okay, last example before I get back into the ROM stuff is we're going to look at a 3D problem. This is the steady Euler equations flow over a cylinder. Here's our mesh that has only 500 tetrahedral elements. We're using polynomial degree 2 for the solution and 2 for the mesh. And this is where we start. I mean, you can tell that this is almost a comically bad solution on this course of a mesh when you use first order finite volumes. And then after about 30 tracking iterations, we get this bow shock tracked pretty well. And I'm now going to just look at the shock layer, removing all of the constant flow outside of it. And you can see that we've got high order approximation of the boundary, of course, but that's just from mesh generation. But we have the high order curved approximations of the actual bow shock that comes from the optimization approach. Okay, so that was it on my first part on implicit shock tracking. We formulated it as an optimization problem over the DG solution and mesh coordinates. We get these accurate solutions on coarse meshes and optimal convergence rates, and then the high order methods they exaggerate the benefits of tracking discontinuities. And that's these kind of takeaways are what we're going to port into the model reduction setting. So if we go back to our example, I can play the first couple things again. So this is where we were at when we started, is that we were trying to approximate the blue with just the black snapshots, and we got the red. So what we're going to do now is we're going to now apply some of these same ideas. We want to deform the domain. I've been talking about it as a mesh, but it's really an underlying domain deformation to align the snapshot, the shock in the snapshots, with the discontinuity. Okay. Now the idea is that within the DG setting, all of our elements are in some sense created equal, and they go to piece them together to cover the full mesh. But in this setting, each one of our snapshots is covering the full mesh, and we kind of want them to work together. So, which one should I pull? Should I pull this one over here? Should I pull this one over here? If you do that approach, you're only going to be able to use one of them, and it takes away kind of the point of the training. So what we do instead is we map all of these to a common reference domain. It's going to be a different mapping applied to each one, but they're going to, and then we are going to do it such that all of these shocks, discontinuities, whatever, align with each other in a fixed reference domain, using the same ideas of an underlying mesh domain deformation. In this domain, there is no convection-dominated nature of the solution. We've removed that. So now we're going to approximate the shock using these basis functions, and it's not moving now. So everything's kind of in the right spot. And then we just push it back to where it was in the physical domain. So that's the idea behind the approach, and that's really how that's how it connects to what we did with the implicit shock tracking for DG. So to take this idea a little bit farther, what I have done is I've just plotted one single basis function that's going to be sitting in a reference domain here, just some cutoff Gaussian thing. And then I have some smooth mapping. And by composing these things together, you can move this shock anywhere you want to. That's kind of what I've already demonstrated in some of the previous examples. But you can, that's what this bottom example here is. By just different values of tau, you can put this shock anywhere you want it in the domain, with everything being smooth. This works in higher dimensions too. I have some sort of a solution here that's got it's kind of centered in the middle of this domain, and then I'm showing some sort of underlying mesh. We apply some smooth domain deformation to it, and we can move the peak over to the right. Right, so that's kind of what we can do this. These domain deformations can move features around. All right, so now to actually start formulating this at a more detailed level, we're going to now write down our physical domain, omega, as the result of a mapping applied to a fixed reference domain. So the idea is that my conservation law is going to be posed in my physical domain, omega, whatever the domain is that you care about. But we don't want to solve it there. I want to solve it on a fixed reference domain, because in the setting that I talked about, where I'm going to be applying a different mapping to each of the snapshots, that means I'm solving on different domains. It's going to be still the same boundary, but the interior is going to be morphed in different ways. So I don't want to deal with that. So instead of this, what we're going to do is we're going to introduce a fixed reference domain, and we're going to recast the conservation laws on that reference domain. That's the fundamental approach here. This is the exact same thing that we do in the shock tracking setting. I just didn't really introduce it at that level because it was not really a necessary detail. Here, it's a more of a necessary detail. Okay, so now here's the outline of the approach. So that we're going to say that we're going to start with our discretization, which is going to depend exactly the same way. It's going to depend on our high-dimensional model solution, U. It's going to depend on the coordinates of our mesh, and now we've added in some sort of a parameter. And we're now going to, but this is all going to be posed in the reference domain. So this U means the state vector in the reference domain. X is the mapping to the coordinates of the physical mesh, etc. So our offline plane is going to go as follows. Given some collection of training parameters, we are going to determine our solution in our reference domain as well as our mapping. These are going to be tied to the current parameter that we're looking at, such that the dominant features align in the reference domain, exactly the way that my little schematic in the beginning. We want them all that feature to be in the same spot. So we can compress the snapshots, and then we can do the approximation of that domain and then just push it back to the physical. So then the next thing is going to compress the snapshots. The compression is a lot more effective when there's not discontinuities moving around. And then finally, we're going to actually reduce the mesh degrees of freedom, because in a ROM setting, we don't want to have to move all of the nodes of the mesh independently, because that way there's potentially a lot of them. So we want to reduce that. And then last thing we're going to do, that's offline. Then online, we're going to, given a new parameter, we're going to determine the reduced order state and the reduced order mesh, and then we can just reconstruct our full mesh and state. Okay. Go on. So here's what the offline procedure looks like. So we're going to start by just, we're going to be given the first, whatever our first parameter is, we're going to just solve the DG equations on that mesh, and we're going to take our first mesh as our, whatever our reference mesh was. So we don't need to do any kind of anything fancy for the first parameter. It's just what we're using to seed our iterations. And then after that, we're going to solve something that looks exactly like the shock tracking problem that I introduced 10 or 15 minutes ago. But it's going to still have your high dimensional model as a constraint here. And you're going to still have a mesh term out here. The one difference is that we're not going to be minimizing this enriched residual, which it doesn't really have any sensitivity to which elements align with the shock. We want to make sure that all of these different snapshots align in a reference configuration. So what we're going to do is we're going to use the projection error of the projection error, essentially, onto this basis. Because the idea behind that would be that when the snapshots have their feature aligned, the projection error will be smallest, and that's what the kind of the idea behind using this. And then we're just going to add on the new solution to our basis, and then just keep going until we're done. And that's essentially the offline procedure. So the reason, again, that we do this is that I'm just going to do an example before and after alignment. Before alignment, we have, just a different example now, is that we have some sort of diffusing or some steepening and it's kind of waning shock that forms here. If we use these snapshots and we look at the first Pde modes, here's what you get. But then if you look at the singular value decay, it's very slow. This is the whole Kolmogorov in-width barrier that we hear so much about. And if we look at the number of snapshots that are required to reduce this to 10 to the minus 3, 10 to the minus 6, or 10 to the minus 9, I mean, it's a ton. If you instead you align these all into one spot, and then you do the look at the first Pde modes, you have that dominant shock captured in your first mode, and your snapshots decay extremely quickly. You get 10 to the minus 3, 10 to the minus 6, 10 to the minus 9 in like 10 vectors here. So this is just more motivation for why we actually go through the pain to do the offline alignment in the first place. Okay, so then online, the problem is going to look pretty similar, but now what we're going to be doing is we're going to essentially we're given a new parameter, and this should be a mu star in here, sorry. We're going to be minimizing our HDM residual over our reduced coordinates for our solution, as well as over our reduced mesh. So people that are familiar with model reduction are used to seeing these kind of minimization problems, but usually you're usually only minimizing over the ROM state. We are simultaneously, in the same spirit as we did with shock tracking, minimize over the state and the mesh. And then we can, of course, reconstruct this. We are working on this now. I don't have any results in this paper about how to extend this with hyperreduction techniques. It particularly fits well within the empirical quadrature type procedures like ECSW and EQP. So I want to just do one last quick example on what this approach kind of looks like in a kind of a very simplified setting. So to do that, I'm going to introduce a one-dimensional domain mapping. So here's my undeformed, here's my deformed, and I'm going to take everything just as linear combinations between these two. So this would be my mesh parameter s equals 0. This would be s equals 1, and then everything would be in s between 0 and 1 would give you intermediate deformation. So this would be s1/2. Now what I'm going to do is here's my high dimensional solution snapshot on the left. This is going to be, just comes from some solution of some advection diffusion configuration. And then this is my training, one single training point. And what I want to predict is this one, where I've changed some of the flow directions parameters, and now the peak is concentrated here at the right. And I want to use this one basis function to approximate this configuration. Obviously, with standard model reduction, it's not going to be a great job because the peaks aren't aligned. But that's kind of the point, is to demonstrate what you get by also optimizing over the mesh. So again, if we do standard residual minimization, this is what you get. I'm showing the mesh here to show that it's not deformed at all. Now, if we also do this implicit feature tracking where we simultaneously optimize over the mesh and the state, you move the mesh to the right and you move that peak over. You pull that peak over. Now, the more interesting thing is on these contours. So right here, what I've done is I've drawn the contours of the error with respect to the high dimensional model versus the reduced basis coefficient, because there's one of them, right? So 1D basis, as well as the domain mapping, because there's one. That's why I was insisting on a 1D in both, so I could plot these with contour plots. And then over here, I did the exact same X and Y coordinates, but here I'm plotting the residual norm. So if we look at the right to start with, when you do standard residual minimization over just the state, what you're doing is you're freezing the domain mapping to be 0 and optimizing along only this line. And that minimum falls right here. If you expand your space and allow it to optimize over the mesh, you actually find that the real minimum or the true minimum in this expanded space lies way over here. So now if we see what this looks like on the error plot, you can see that you're, by restricting to this s equals 0 line, you're stuck in a pretty high error region. But by, now residuals and errors don't necessarily, they're not the same thing, obviously. So we're not getting to a minimum of the error, but it's falling in the low error region of this diagram, which is really the point of expanding the space and optimizing over both. Okay, so now we're going to look at two examples. The first one is a beautiful example that Tommaso introduced in his 2020 paper. That's just a very nice parametrized advection reaction equation, where it's got three parameters, but the main parameter is in your flow direction. It's what changes the kind of the direction of your primary steep feature that you've got here. So just showed a few different snapshots, and we're going to apply the implicit tracking procedure to this problem. So the first thing that we're going to look at is the snapshots that we generate. So we generated a few different snapshots here. This is just the one that we start with, right? That reference configuration that we start with. And then we have two different ones based on whatever our parameter configurations were. And you can see that if we're in the physical domain, you have your mesh that's kind of moving around. This is just kind of plotted to view so you can see what the domain deformation looks like. But you have here and then here, you can see how the elements that were originally aligned now dip down to a line there, or they dip up to a line there. And then, but the key thing here is that if we look at this in the reference domain, that's what we have down here for each of these snapshots, and the primary discontinuity is always in the same spot, or roughly in the same spot, which is going to improve the compressibility of the snapshots. Now, if we look at the POD modes, the top is if you don't bother to do any sort of alignment. And what you see is that these are just the first three POD modes. All of the energy of these modes is focused on trying to advect that feature across the domain. And that's where, but you don't get any of the really detail elsewhere. I mean, you get some, I guess, but it's not really it's much less dominant feature in these basis functions. Whereas if that feature is not moving, all of the higher order, the higher order modes, the higher modes, are going to be focusing on these kind of auxiliary features and not having to worry about that main discontinuity, or its steep feature in this case. So that's kind of the visual representation of what we're trying to do here. Now, if we look at just a quick little study, so what I did here is I just looked at a 1D parameter space by freezing the second and third parameters and only varying this more difficult parameter that moves the discontinuity around. My test set that I'm going to be testing both a standard ROM and a ROM with implicit feature tracking on contains 100 samples in this 1D space, and the error metric that I use is the maximum error out of all of those 100 test points. And what I'm going to do is I'm going to grow my training set, because the whole point of trying to do this is trying to use limited training. Because, I mean, to be honest, if you didn't care about what the training cost was, you don't really need to do any of this, because take enough snapshots and you're eventually going to get something that's okay, right? So the whole point here is being able to do this for limited training sets. Okay, so that's what we're doing. We're growing our training set from containing 1 to 2 to 3, all the way up to like 40 points. And what we see is that if the black is the ROM and the blue is the implicit feature tracking, that for really small training sets, like less than size 10 here, on the size 1, 2, 3, 4 range, and there's a big difference, or almost an order of magnitude of reduction in error between the ROM and the ROM with implicit feature tracking. And that you have diminishing returns when you have large basis functions, as you'd expect, because the ROM is you're getting a decent sampling of that discontinuity now, how it's moving around, and getting a pretty good approximation of it. So that's the first study that we ran here to see the kind of the benefits of this, particularly in the limited training regime. Now, if we look at another study where we're actually opening up and considering the whole 3D parameter space now, and we're considering a 5 by 5 by 5 sampling of that as our test set, and taking, again, the maximum error over that, if we do a training set that only contains one snapshot, literally one point sampled from the very center of that parameter domain, not going to expect too much out of this because of how limited the training is. With just a standard ROM, your maximum error is 59%. But with the feature tracking, it's still, I would say, unacceptably large at 26%, but it's still a pretty dramatic reduction down. Now we do the next one where we just do a 2 by 2 by 2 to give us 8 snapshots. Then the ROM is still at about 24%, which is roughly what the implicit feature tracking was at with only 1 snapshot. But the ROM with implicit feature tracking for the 8 snapshots goes down to 5-ish%. And you can just see this was a kind of a representative example we took. This is the HDM solution. This is the ROM, where you see kind of you don't get the discontinuity. It's kind of smeared over the kind of the range where it's varying. And then the implicit feature tracking removes that, but it's not perfect. I mean, you can see these features down here certainly are not being captured that well, even with the ROM with implicit feature tracking when you have limited training. But you get the primary, the dominant features out. All right, so I'm just about out of time. So one last quick example was just transonic flow over a Noc Airfoil. So we're going to be, this is where we're actually going to combine implicit feature tracking and implicit shock tracking. So that's where we're going to, our reference CFD solver is going to be implicit shock tracking. So actually the meshes that I'm going to be using here are really coarse. I only have actually 127 element mesh. But we'll look at the first two. These are going to be the snapshots that we're going to get with using this implicit feature tracking. We have Mach 0.8 here, we have Mach 0.87 here, and then we have a training configuration which is Mach 0.85. And this is our online approximation, and you get a reasonably good approximation. I haven't compared to HDM yet. I'll do that in a couple slides. Now, if we look at without the mesh, you can see what these features look like. The shocks are of varying position along the airfoil, and they extend a different amount into the domain before they become smooth. Now, if we look in the reference domain, kind of go back and forth between those again. So this is in the physical domain. If we look in the reference domain, all of those shocks are kind of in the same spot. And you can see that better if we look at slices of the solution. So in the physical domain, we have this shock as we change our Mach number is changing kind of all through here. But if we then look at these things in the reference domain, boom, all the shocks line at this one spot, which is exactly what we wanted to improve the compressibility and approximation of these features and just to completely avoid any sort of staircase type discontinuity approximation. And then now if we compare the implicit feature tracking at the two training configurations as well as at the online configuration, you can see pretty good agreement between the two. The blue is the HDM, which comes from implicit shock tracking, and the yellow is the ROM with implicit feature tracking. Okay, so that is pretty much everything I wanted to say. So just to summarize, we introduced this implicit feature tracking, which is really, I think of as implicit shock tracking, ported into the model reduction setting. It leads to, we align features in snapshots to improve the compressibility. We do residual minimization over simultaneously, the same way that we do with shock tracking, simultaneously over the state, the reduced basis state, as well as the domain mapping. And then this can lead to accurate solutions for shock-dominated problems with limited training. With that, I just want to acknowledge my funding as well as my students here at Notre Dame. TENS has done a lot of great work on shock tracking, and Mars has done a lot of great work on the ROM implicit feature tracking. So with that, thank you very much for your attention. I'd be happy to take any questions.
Thank you. Thank you so much. It was a wonderful talk. I loved it. Okay. Thank you so much for great talk, Matt. Let's have a Q&A session. Yes, there's a clap from Grace. All right. Okay. The questions are coming in chat room. Okay. First question from Henry. Thanks for the talk. Do you know if this technique has been applied to modeling dislocation dynamic in solids, wherein the dislocation points have diverging strain fields, or in your opinion, when looking at the problems such as such high resolution, one might as well just do atomistic molecular dynamics? Atomistic, yeah.
Yeah. So I haven't really done much on applying these kind of techniques to anything in solids yet. It's something I'm interested in doing, but I haven't done anything there yet. So I really don't know what to expect out of it. But it would be interesting, and I do think that especially the implicit shock tracking approach, if you start with implicit shock tracking, it's very natural to build on this implicit feature tracking ROM approach on top of it. That's kind of why I did that for the airfoil, this Noc Airfoil case. So yes, and as far as when looking at such high resolution, should you do atomistic molecular dynamics? That's a little bit beyond what I can kind of, I guess, give a recommendation on, because I don't really do any work in atomistic. So I'm just going to probably skip over that, because I just don't really know.
Okay, thank you. Next question is from Rahul. I suppose this method be expected to extended to be any problem where there might be a sort of discontinuity in the computational domain. Please correct Rahul if he's wrong.
Yeah, no, so that I agree with you, actually. I think that because this idea is very PDE agnostic in some sense, where I wrote this down really. The kind of the point of departure was the optimization formulation: minimize f subject to r of u comma x equals 0. So if you can kind of write your PDE in that form, it can be, essentially, you would think you could use this kind of an approach. Now, of course, the details and these objective functions should scale, or should extend, as at least ours are a little bit tailored to finite element settings. But if you're using a finite element setting to do these types of simulations, it should extend. Again, I haven't done them, so I don't exactly know what the issues would be that would arise. But at a high level, the formulation is not really tied to conservation laws in particular. They are tied to a few things. You need to have the ability to move your mesh around, obviously, but you also need to be able to have inter-element jumps. So that means you wouldn't be able to kind of combine this with the continuous Galerkin method. You'd have to have like a DG method or a finite volume type method that supports those inter-element jumps. But with those two things, I think there are other applications that involve discontinuities that could be explored.
Okay, next question is from Pearson. Great talk, Matt. Do you have any opinions on using cuboid versus simplicial meshes for this kind of method?
Yeah, that's a great question. So I've used only simplex meshes so far, and the main reason is it's something that I glossed over a little bit. I mentioned it, but I glossed over it. Was to do any of the more complicated shock structures, like those triple points and things like that, and even the 3D problems that had the simple shock structure, you can't fix the topology of your mesh. It's something that I fought with. I wanted to fix the topology of the mesh because I don't like doing meshing type operations. I wanted to fix the topology of the mesh for like a year, and then eventually just had to give up on it because you just can't really track things if you do that. At least not complicated things. So the element collapses are critical to be able to make this work. And the reason that I brought this up is because element collapses are I don't want to say trivial, but they're easy, they're straightforward. You can do them for any polynomial degree, you can do them for any dimension. Like in our code, we have a dimension independent simplex collapse where it would work in 8D because of the known structure of simplex elements. So it's different with hypercube or cuboids in general, because if you collapse an edge, you're not guaranteed that the volume goes to 0. So you kind of have to decide what to do at that point. Do you continue to collapse edges until the volume does go to 0? Do you try to work with degenerate elements? It's just not obvious exactly how you would want to handle that. It's something that I'm interested in doing because a lot of people, and I'm working hypersonics, they really like to use hexahedral meshes because of just they give better approximations to surface heating and things like that. So it's something I definitely do want to look into, but it's more of a difficult meshing problem to remove hypercubes out of your cuboids out of your mesh.
Awesome. Let me inject my question, by the way. There are two more questions, but regarding the element collapse, in the context of your reduced model formulation with the shock tracking, probably you don't allow element collapse there because.
Right. So, okay. So that's a good question. So I do allow element collapses to get our reference mesh, right? I talked about how we need a reference domain. So we do implicit shock tracking with its kind of full form to get that initial reference mesh. And then once we do that, then you're right, then we don't allow element collapses to move to align all of the different snapshots together, because then you'd be collapsing elements and you'd have state vectors that don't kind of match up and things. So yeah, so you can't allow it, but it's a different problem in that case. We're not trying to align a kind of general unstructured method with a very specific discontinuity. We're trying to take that discontinuity and push it, right? So that's why we're kind of okay freezing the mesh for that step.
Okay, that makes sense. Okay, let's move on to next question. Next question is by Kevin. Is there a way to tie this into time-dependent problem?
Yeah, so yes, there is. And so there's two different ways to do it. So the first way that we have a paper that's on archive right now for the shock tracking version is just using standard method of lines. And where you do that, you replace you basically just you pose a shock tracking problem at each time step. And you use an ALE formulation to be able to handle the mesh deformation. And that's exactly, and you could extend that approach to ROMs. And so instead of having, R of u comma x equals 0, you would have a mass matrix with a u dot term that you discretize, let's say, with backward Euler or Runge-Kutta or whatever it happens to be, and then you use it in that setting. It is inherently built really for implicit methods, though, because of this optimization formulation kind of makes it so you have to do solves anyway. So it would be hard to justify this with an explicit method. I haven't really thought too much about it other than I just don't quite see a way forward with that. But certainly if you're doing an implicit method, you could do that. But the problem with that though is that if you have a shock that moves a large portion of the domain, you really have to have, if whatever you track, let's say whatever elements track the shock at time 0, you kind of have to pull those elements along the whole way, or you have to do some more complicated solution transfer between meshes as you kind of pass the shock off between elements. So what we've done so far is you would just track at time 0 or at whatever time the shock emerges. You would do the tracking, and then it's the same edges of the elements, the same elements that track the shock all the time. Now, of course, if the shock moves a lot, then you can really screw up your mesh. So we don't really do the method of lines approach that much. What we do is we do space-time, where we just, no matter what, even if you have a time term on there, you still lump it inside your, you just think about the problem in one higher dimension. And now the time derivative is just one more dimension in your divergence term. And you solve it in space-time. And we don't have to do the whole space-time at once. The problem that I showed, the SOD problem, we did all of space-time together. But we're working on approaches where you just do slab by slab by slab. So it kind of looks a lot like time stepping, but you are solving a problem in one higher dimension to do it, albeit over a small little slab. So those are the two ways that we do time-dependent problems. They both have their, like if the method of lines approach would work, meaning your shocks aren't like doing crazy things, bouncing all over the domain, then that would be the easiest and probably go-to option. If you have really complicated things where you have a shock that forms and then bounces off something and intersects and goes all the way across your domain, then I just don't see it really a solid path forward with the method of lines. So that's why we're investing in the slab-based space-time approach for that.
Okay, sounds good. Related to that question, so how about how do you envision, extending your method to turbulent flow or like mixing problems due to the instability?
Yeah, so turbulence, I haven't thought too much about turbulence yet. It's certainly going to be an issue. I mean, the main issue with it is going to be, the turbulence is going to kick up some unresolved features, obviously, because of the scales that are involved. So how will the sensor, the objective function that we have, respond to that versus discontinuities is not obvious, because it could just cause the mesh to just freak out during all these where all these turbulent features are. So I'm not sure. I guess overall, but what I've seen, I guess it depends on the regime you're in, but shocks are usually significantly stronger features than the turbulent vortices and eddies and things like that. So I still think that we could probably, somehow cut off the residual when it gets under a certain point, so it kind of ignores the turbulence, and then still salvage it. But yeah, that's something that is certainly an area to look toward.
That's a good idea. Okay, next question is by Harshit. Thanks for the nice talk. How time consuming is the optimization step, and how do you guide the choice of regularization parameter gamma?
Yeah, okay, so that's a great question. So the optimization step is more expensive than doing the just a standard. I mean, if you were to compare it side by side to, one step of our SQP thing, and by the way, it's the same optimizer that we use for the ROM setting. It has the exact same structure. We use the exact same solver for it. One step of that would be more expensive than one step of just a standard, pseudo transient continuation or Newton solver without moving the mesh, because you have more degrees of freedom. So yes, it's more expensive, but where it doesn't really affect us that much is that we are using much coarser meshes than you would use if you had to do this without moving the mesh. So that's kind of where, I mean, our meshes, depending on how many dimensions you're in, they can be, 1, 2, or 3 orders of magnitude coarser than what you would need. And actually, it's something that I'm not sure if I'm proud of or embarrassed of, that all of the results that I showed in all of this talk, but especially in the shock tracking section, that was all done with MATLAB. I mean, we were able to do 3D supersonic flow and over that cylinder in MATLAB. We were able to do that flow through that scramjet in MATLAB, and we just use direct solvers and things. So it's not like they're cheap to do, but it's, because of how dramatically you can reduce the number of degrees of freedom needed when you track shocks, that you can do these more complicated problems on, not traditionally high performance computing platforms. And we are extending it to, domain decomposition and fully, full implicit solvers and things to be able to push to harder problems and more complex ones. But I guess the summary is, yes, they are more expensive, but we use coarser meshes, so it doesn't really affect us. And then the second part of the question, I guess, is how to choose that regularization parameter. There's a little bit of tuning that goes involved with that. But what we do is we adapt it. Actually, we have a few different parameters in here, and they adapt as they go. So, for example, this one is how we weight between the mesh regularization term and not. And we start it by not treating the mesh. We basically, what we do is we adapt the lambda parameter such that those two contributions are roughly balanced throughout the optimization. We don't let it adapt every single iteration, otherwise you would not be converging. You would not be convergent. We only allow it to adapt at some frequency. And then once the residual drops below a certain value, meaning you're kind of in the convergent regime, we disallow the adaptation of the parameter. So it's adapted to balance those two terms, and eventually just cut off because we don't want it to impede convergence.
Okay, great. Thank you, Matt. Another question from Pde. Great talk at a high level. By moving the mesh with solution in a way, a spatial context is provided in the training for neural network to be able to better capture the feature or dynamic modes despite convection. Some works presented at DDPS used graph techniques to provide spatial discretization context for training. Can similar graph techniques can be alternative?
Yeah.
Yeah.
So yeah, in 1 second, let me read that again.
Yeah.
Provided in the training for neural network to be able to better capture the feature or dynamic modes despite convection. Yeah, so those I didn't do much of a literature review here, but yeah, that certainly is a way to do this. I mean, basically the main takeaway point here is that you can't just use the kind of the standard old linear basis approximation if you really want to be able to use limited training and be able to and approximate these convection dominated problems. So in somewhat, you need to make your basis nonlinear somehow. The way that I chose to make it nonlinear is I composed it with this domain deformation, and that essentially made for a nonlinear basis. There's other ways to do it. The neural network approaches. Young Su's worked on some. Kevin Carlberg's worked on some. There's lots of others that have worked on these kinds of approaches, and that certainly is an alternative to doing this. That's this approach, I would say, preserves a little bit of the kind of standard structure model reduction, and we do actually, once we're in the reference domain, we do use a standard linear approximation. Because that's the domain where everything's aligned. So that's where we are using our linear approximation there. So it does preserve a bit of the kind of standard model reduction structure, where you can apply standard hyper reduction techniques, for example, that you would that would have to be, I would say, significantly modified to fit into the neural network framework. But no, you're absolutely right. This is not in any means the only way to do this, and there have been other people that have done these kind of approaches. Tommaso has done similar approaches. Juan has done similar approaches. I mean, that there's lots of variance on these kind of techniques and these ideas to be able to do convection dominated problems. All of them have something in common, being either doing some sort of additivity or somehow making the basis nonlinear.
Right. Let me add some comment to that. I mean, yes, I personally have a research experience of developing a neural network solution representation for reduced order model context, but I do think that the maths, the method he presented today is very advantageous in a sense that the neural net, if you have any experience of training the neural net, it's a lot of trial and error procedure, and the training itself can be very computationally expensive. But on the other hand, POD is very simple. Like, I mean, a lot of SVD algorithms are out there available right for you, and then just simply you apply this SVD and then taking advantage of this the linear subspace solution representation with very cheap, relatively cheap training cost, and then still use that in the context of the convection dominated problem. This is really good work. But as Matt mentioned, that there are other methodology available. Okay, with that, I don't have any questions from the Q&A chat room. But okay, I mean, please go ahead and post your question if at the last minute if you have one. But I just want to comment one more thing about the Matt's presentation. You mentioned that the model order reduction can be considered as a extreme case of the higher order model. I really like that comment. Actually, I try to advertise that concept of the model order reduction within the Lawrence Livermore National Lab, but I was not that successful selling that idea yet. But external the scholar coming here and then saying those kind of comments will definitely help. Thank you so much, Matt.
Yeah, of course.
Okay. All right. I don't still see any questions in the chat room. I guess we can add John. Well, Matt, thank you so much. It was a great talk, and I learned a lot. And I hope you will continue to go this direction and advance, much more for more complicated problem and more practical and engineering problems. And please keep us posted with the progress. Yeah.
Thanks so much for the invitation. Really appreciate it.
Yeah, no problem. And also, I hope that audiences take advantage of as a first exposure to Matt. If you haven't seen Matt before, please contact him and then ask question and email him. I'm sure he's gonna reply to you with a detailed explanation and reply, and then may bring up the collaboration, right? So that's another motivation for this seminar series. So okay, with that, let's add John, and thank you everyone. Thank you, Matt, again.
Yep. Thank you very much.
All right. Okay. Bye, everyone.
Bye.